She's very talented.
Women are very good at multitasking.
Make it more complicated.
Okay. Let me say this again then, because this is important, and it's something that Schwartz for some reason skipped. Probably, here's the TA, 3 minutes early, in fact. Suppose we have a derivative with respect to a prime coordinate. In other words, we've gone from x, dx's to some x primes. And this is what the relativists love to call a general coordinate transformation. Equivalently, it's an arbitrary coordinate transformation, just as long as it's 1-to-1. And, you know, not completely crazy. I mean, it's this side of Lomas. Okay. Not the math department. Then, just by the chain rule, this is partial with respect to xj, partial xj, partial x prime I. Okay. I'm using I instead of mu nu because I think since we're not Greek, it's easier to look at I and j and k than mu and nu and lambda and sigma. Okay. So, the thing, for an arbitrary transformation, x to x prime, this is the way derivatives transform. And then what we say is, this is the definition, this defines covariant. On the other hand, dx prime I would be dxj of partial x prime I, partial xj. And that's a difference because the prime is down here and it's up there. And also the i's and j's switch. And this defines contravariant. Okay? And notice the index is, well, it's up on the x because dx is contravariant, but we write this as d prime I. So it is a lower index, covariant. So derivatives are covariant always. Differentials of space-time are always contravariant. That defines contravariant. And these two things define contravariant and covariant. Then what's clear is that d prime, the differentials times the derivatives are invariant because the differentials go as x prime I partial x, let us say k, dxk, and then this one is partial x, let us say L, partial x, well I could have done j, prime I, dl. This is of course the same thing as partial xj, partial x prime I dj. And now, if you just, we're summing over I, of course, so you couple this one with that one, and you see that this is just, by the chain rule, it's partial xl, partial xk, dxk, partial l, so this is delta lk, dxk, partial l, and so this is just d xk, partial k. So this inner product is intrinsically invariant always with arbitrary coordinates transformations. And it's an example of what's called a contraction. Because you see what they do in what we do in general is we say any vector ak with a lower index is covariant if it transforms this way, and any vector BL is contravariant if it transforms this way under coordinate transformations. And then just repeating this calculation, you see that AK, BK, summed over K, of course, because we're using the Einstein summation convention, is invariant. So that's the basic idea. Now, one of the ideas of relativity is that we should have equations that don't refer to any particular coordinate system, because of course if the equations did depend on the coordinate system, they couldn't be right because we don't know which coordinate system is right. And that was one of Einstein's insights. And in fact, the standard model is another variation on that same insight. It's that what we call the fields shouldn't matter. We should have we should be able to change the names of the fields as we go from place to place. And that's called the gauge transformation. All right, so for example, if dxi is, let us say, xi minus yi, and x and y are two adjacent events, then we should be able to make something dxi, dxj, gij. We should be able to have something that makes this invariant. And so that, in other words, is equal to dxk, dxl, gkl. And indeed, if g just transforms as indicated by these two lower indices, that is to say, if g is just a tensor that is doubly covariant, then this is a double contraction and this will be invariant. And okay, now what I want to do now, of course, is leave the general context of general relativity and just go to special relativity, because that's the subject of this second chapter. And there, the idea is that space is flat, and so this G is a constant. And in fact, the dx's, we don't need to talk about differentials because we're talking only about transformations that are of the form x prime I is Lij xj. That is to say, they're linear transformations in which the L's are just constants. And now if that's the case, then what you can do is you can make if you want, a general coordinate transformation and just make this G a constant. And you can always do that, even in general relativity, you can do that around any point, a tiny neighborhood of any point. But then if you do that around a tiny neighborhood of any point, and then you say, well, space is flat, well, then it's the same everywhere. And in that case, it's just some constant. And then what you want is, let's see, maybe I should have some of these. All right, let us just say, let me use A and B, because that's what I did in my notes. Actually, I had a C here. Okay, so these are the constant transformations. Okay, so we're talking about, oh, by the way, when you make this general coordinate transformation, you can then take this G and you can diagonalize it, and you can arrange that the elements on the diagonal are plus or minus 1. And so then basically you have, you can have the choice 1, minus 1, minus 1, minus 1. And of course you have to have all these space things the same, otherwise you wouldn't even have rotational invariance. And so then the choice is this going to be minus 1 also, or is it going to be plus 1? Well, if it were plus 1, it would be, I mean, minus 1 would be kind of crazy because it wouldn't even have Galilean relativity. And so that's what this thing is. G0 or eta then is that diagonal matrix. And now, what are the linear transformations of space and time that keep this thing invariant? Well, it's, and this will illustrate also how up and down indices and so forth are related. It would be, we want x prime A, y prime B, eta AB, and that's LAC, XC, LBD, YD, eta AB, to be equal to XC, YD, eta CD. So then, say, differentiating with respect to x and y, what we get is the rule eta, this is the flat space metric. And yeah, I'm violating my rule to avoid Greek. I don't know, it's just hopeless. Eta CD then has to be LAC, LBD, eta AB, and that is the definition of a Lorentz transformation. If we make this look more like matrix multiplication, then we have AC, eta AB, and then over here, LBD, and now this A is in the wrong place. It's a row index. We want it to be a column index. So we make this L transpose CA, eta AB, LBD. And so now the matrix rule is eta is equal to L transpose eta L. So that defines a Lorentz transformation. Now notice, in this business, the first index is a row index. If you want to go from tensors to matrices, the first index is a row index, but you can only do it for tensors of rank 2. First index, row index, second index, column index, whether it's up or down. Whether it's up or down tells you how it transforms under coordinate transformation. And now, of course, eta squared is 1. And so, if we have eta is L transpose eta L, then 1 is eta squared is eta L transpose eta L. And that means the L inverse is eta L transpose eta, which is kind of an interesting relationship. Okay, so I'm going to now get back much more closely to the book. Let me emphasize here in relativity, especially special relativity, but maybe even more especially general relativity. Invariants are your friends. They're the things you want to focus on because they're simple. They're the same in all coordinate systems. And so let me give you, and of course, what are invariants? Well, things that are contracted. And so, for example, if we have a free particle of momentum P, then PA, which is P0 squared minus P vector squared. In other words, this is PA, eta AB, PB, and this eta AB just flips the sign of the space, so you get a minus sign here. And so this is E squared minus P squared, and that's M squared. I've set C equal to 1. If you put the C back in, it's, well, it's still E squared, goodness, is minus P squared C to the 4th equals M squared C to the 4th. P squared c to the 4th. You want p squared c squared?
Yeah.
It may be.
That's why I said equal to 1. Yeah.
I set it equal to 1. That's why thank God we can set it equal to 1.
P and M.
Well, I just don't remember, okay. From the dimensional units there, we have, what will we have? Oh, Christ. All right, it would be m squared L squared over T squared. So that's MV, M squared V squared. And then we have L something over T something. And all right, let me trust you. Put a square in a square. So that's yeah, that's energy squared. Yeah, you're right. Candy? No? Yes? You sure? Thank you. All right. So this is one invariant which is really useful. Another invariant that's very useful is obtained by contracting the derivative. So this is a, if you want, a contravariant derivative. But in effect, it's dA eta AB dB, say. Well, I've gotten it backwards. But anyway, whatever it is, it's d0 squared minus grad squared. And we often call this box, because this is sometimes written as, in other words, this thing is called the D'Alembert, and it's also often written as triangle. And so people doing particle physics, having derivatives in 4 dimensions, go from triangle to box. That's the deal there. Now,
kindergarten algebra.
Hmm?
It's a kindergarten algebra. We're going now from square to box.
Well, from triangle to
Triangle,
box.
excuse me. That made no sense the first thing I said.
Okay. Now, I know when I was a graduate student, one thing that really confused me was where the hell the minus signs were. I mean, I knew they were there, but I wasn't quite sure where they were. And so let me try to clarify that for you. So we have XA, this is TX, and PA or PU, if you want, is EP. All the signs are positive if the particle is going in the positive direction. Derivatives. Now, derivatives come out positive if they're in their natural place. Remember, the reason why the A is up is that differentials are contravariant, which means up, and X is just a big differential. Because we're in flat space, it doesn't matter. Derivatives, on the other hand, are naturally down, and so this is D0 grad, and D up is D0 minus grad. And of course, I'm doing all this in Schwarz's metric, so every now and then I'll screw up the sign. Now, what about X lower a? Well, X lower a is T minus X. P lower a is E minus P. And, all right, there, that's basically it. That's the whole story. All right, so we've been talking about the ordinary Lorentz group. This is called the part of it that's connected to the identity is called the proper orthogonous Lorentz group. Orthogonous means we don't screw around with the sign of time. And if you want to screw around with the sign of time, you use this, minus 1, 1, 1, 1. That's the time reflection or time reversal matrix. And by the way, quantum mechanical time reversal is spooky. Very spooky. Parity, this is 1, minus 1, minus 1, minus 1. Of course, this is the same thing as eta, really. And that's the parity operator. And of course now, or matrix. Now, we have, of course, this definition of timeline. That means that the x minus y squared is greater than 0. So in other words, x minus y 0 squared minus x minus y vector squared is positive. Space like is the opposite. And let me just write dx squared here. So this is dx 0 squared minus dx squared, and this has to be less than 0 because the space part is bigger. And then, of course, like, that's 0 equals dx squared. And so that's dx 0 squared minus dx squared is 0. So photons go as dx squared like. And in fact, for any massless particle, PA is P0 squared minus P vector squared is actually 0. It would normally be m squared, but the particle is massless at 0. So the full momentum of a massless particle is light-like. All right. Now I'm going to do some problems. In fact, I'm going to do most of the problems that I didn't assign. I know you'd rather I did the problems I did assign, but...
Well, it looks like you did. At least one of them.
I did?
Yeah. Something about particle creation.
Huh?
Yeah.
Particle creation?
We talked about that last week.
All right, look, I don't. All right, so let me do problem 2.2. The question here is how fast basically is a proton going in the LHC when the LHC is at full moment, at full energy? And of course, so far it's only been up to 8 TeV in the center of mass. I understand that somewhere in another 6 months it's going to be at 13 TeV, and I think eventually we'll get to 14. Anyway, I'm going to use H bar and C equal to 1 so I don't screw up again. So 7, and this is TeV, is equal to m over square root of 1 minus v squared. So that's basically what we've got. And that means then that 1 minus v squared over c squared is equal to, now what is m? M here, if TeV is 1, this is 938 MeV, or let me just say 0.9 GeV, or 0.9 10 to the minus 3 TeV. And so this 1 minus v squared over c squared is basically 1 minus 0.9 squared over 7 squared 10 to the minus 6. And if you work out what v over c is, just using some sort of a calculator, it's 0.99, and there are 8 of these. And then 101 and so forth. Okay. If you want to, though, answer the question, you have to express v over c, or c minus v, in kilometers per hour. And so, of course, c squared minus v squared is c plus v, c minus v. Now, c plus v, that's just 2c, because v is essentially c, so that's c minus v. So basically, what we've got is that this c squared minus v squared is this thing here times c squared. So this is c squared times 1 minus, well, it's 0.81 over 49, isn't it? About 10 to the minus 6. So that's this thing. We have to multiply by c squared. So that gives us c minus v is c over 2 times 1 minus 0.81 over 49, 10 to the minus 6. Well, to find out what C is in kilometers per hour, I just Googled it, and it's 1 times 10 to the 9th kilometers per hour. And so anyway, I worked this out and got 9.7 kilometers per hour. That's what I got for it. I may have screwed up, but that's right. Okay, part B is an illustration of the use of invariants. Part B is what's going on. So that's how much slower, I mean, in the lab frame, that's how much slower each proton will be than the speed of light when the thing is at full energy. The next question was, what is the speed of one proton in the rest frame and the other if the two protons are aiming at each other at 70, each one 70 eV? So what we do is we use these invariants, P plus P squared. Well, I can evaluate this in the center of mass frame, in which case the momentum, free momentum cancels, and that's just 2e squared, and so that is 4e squared, because 2 times 2 is 4. Okay, and then in another, I can also evaluate this in the rest frame of one of the protons. Well, then this thing looks like this: m comma 0, oh, plus, e prime, p prime, squared. When I say square, I mean the Lorentz inner product, energy squared minus momentum squared. Okay, so what is this? Well, this is then m plus e prime squared, m plus e prime squared minus p prime squared. And m plus e prime squared, well, that's, of course, m squared plus e prime squared minus p prime squared, and then plus 2m e prime. Well, you notice e prime squared minus p prime squared, that's another one of our favorite invariants. This is just m squared. And so what we have then is 4e squared is equal to 2m squared plus 2m e prime. And so you see, e prime then is just basically 2e squared minus m squared over m. Well, in TeV units, this is 2 times 7 squared, which is 49, minus m squared, which is essentially zip over m. And so this is 98 TeV squared divided by 10 to the minus 3 TeV. So I'm getting 10 to the 5th TeV. So the energy of the other proton in the rest frame of one of the protons, in the rest frame of one of the protons, is 10 to the 5th TeV. Again, this is not gospel. I mean, I could have screwed up, all right? So you check this. So that is equal to m over square root of 1 minus v squared. And so once again, what do we say? We say that 1 minus v squared is then e prime squared over m squared, and that is then 10 to the 10th over 10 to the minus 6, and all right, I screwed up. One is e prime is, yeah, there's an inverse going on here. Yes, thank you. So it should be m. Yeah, m squared over e prime squared. And and so this is 10 to the minus 16. And so once again, this is equal to 2 times 1 minus v is 10 to the minus 16, and so 1 minus v over c is then a half 10 to the minus 16, and v over c is, of course, that, and so v is c times 1 minus a half 10 to the minus 16. So the speed of light, apart from 10 to the minus 16 divided by 2. Whereas over here, we had c minus v was, it's roughly, oh, I don't know, 10 to the minus 7 or something, So it's all right, so much for that one. Now, the next problem, 2.4, is you're considering the transformation x prime is equal to x0, x1 minus x2, x3. So the question is this a Lorentz transformation? Well, in fact, it is. But why isn't it then thought of as a special reflection like parity and time reversal? The reason is that this transformation, which just flips x2, this can be regarded as parity times a rotation about the y-axis of angle pi. So if you rotate around the 2 axis, say, by pi, you take x1 and x3 into minus themselves, then you hit it with parity, and these guys come up plus, but this one gets a negative sign. So this is that. And this rotation, by the way, this is then parity e to the minus I pi j2 or jy over h bar, if we want to put in the crazy unit for the h bar. All right, any questions? Okay. The next one is Compton scattering, and I must say, let me just take a quick break and tell you, this isn't a joke, this is actually a true story. I don't think I've mentioned this to most of you yet. I spent 2 summers now in Korea at something called the Korean Institute for Advanced Study, and the person who founded it was a professor at Johns Hopkins, a Korean named C.W. Kim. When he was a little boy, Korea was under the occupation of Japan, which started in 1910 and continued brutally until 1945. China was also, unfortunately, occupied by Japan, and also brutally. So his family, to get work, moved to Japan in about 1940 or so. Well, in 1945, he was in school in Hiroshima. And luckily, they had moved grades 4, 5, and 6 out into the suburbs, and so he was in school in a Japanese temple 9 kilometers from ground zero when the bomb dropped. And most of the kids would have been killed if it weren't for the fact that Japanese temples have paper windows instead of glass windows. So when the blast wave hit, it shook the temple, but just blew the paper around and it didn't kill anybody. Maybe a paper cut here and there, but lived through it. And what I must wonder about is what attitude he must have toward other difficulties in life. I mean, what could possibly scare this guy? If when he was 9 kilometers, that's 6 miles from ground zero. And, shook him up a bit, no more than earthquakes. So. Anyway, I just thought I'd tell the story. All right, 2.5 is basically the Compton effect, and well, the Compton effect in qualitative terms. And so what Compton did was shine some X-rays at a crystal of some kind. Now, what kind? A crystal of a light element. So it might have been, I don't know what it used, but lithium or boron or, you know, some light element. Why light? Because a light element has electrons that are not, that are bound by EV rather than KEV. And this thing was KEV, and so we wanted to be able to consider the electrons as free. In fact, that's the answer to the first part of the question. Part A is the X-rays that he used were hard X-rays or gamma rays, and he probably used both. And so we're talking several, maybe hundreds of KeV versus a few EV, and so you can treat the electron as being free. And there's an aspect of this experiment which isn't normally emphasized in descriptions of Compton scattering. I mean, normally you just compute the cross-section and let it go with that, and we'll do that later in the year. But Schwartz's last question actually pulls out something quite interesting, which I'll get to in a moment. So let's go to the lab frame, which is what Compton was in. Electron's initial momentum is m0 because it's effectively at rest. The photon is omega and then some k, where the length of k is equal to omega because, of course, photons are massless. And now this omega, which is k0, which is the length of k, this is p dot k over m. And omega prime, which is k0 prime, length of k prime, is p dot k prime over m. All right. Conservation of momentum, free momentum, tells us that p prime is equal to k minus k prime. So that's conservation just of free momentum. Now we do conservation of energy. The energy of the final electron is its momentum, which is k minus k prime squared plus m squared, it's the 3-vector course, plus the energy of the final photon omega prime is the energy of the electron plus the energy of the photon, initial photon. So we move, the first thing to do is you just move the omega prime over there and square it, and then you have k minus k prime squared plus m squared is equal to m plus omega minus omega prime squared. And what does this give you? This gives you k squared plus k prime squared minus 2 k dot k prime. Well, that's basically the scattering angle there. Plus m squared equals m squared plus 2m omega minus omega prime plus omega minus omega prime squared. These m squareds cancel. The rest of this on the right-hand side is 2m omega minus omega prime plus omega squared plus omega prime squared minus 2 omega omega prime. Well, omega squared, the beauty of these units, natural units, omega squared is k squared, omega prime squared is k prime squared. And so altogether, what we have is omega squared plus omega prime squared minus 2 omega omega prime cosine of the scattering angle, because this is just omega omega prime cosine theta, is 2m omega minus omega prime. Well, I've got all this, I've got some extra stuff here. So let me just say minus 2 omega omega prime, and let's get rid of these guys because they canceled on the other side. And so what you find, let me just skip a little bit of this algebra. What you find is that omega prime is omega times m over n plus omega times 1 minus cosine theta. Okay. So when is omega prime biggest? Well, it's when this thing cancels, this thing is 0. When theta is 0, cosine theta is 1, and the m cancels the m, and omega prime equals omega. So the X-rays that go in the forward direction have the same frequency as the initial X-ray. On the other hand, as you go to pi, this becomes a 2, and so the frequency is omega times m over m plus 2 omega, so it's less. And the amount that it's less is by something that depends upon the initial frequency. So Schwartz asked for a rough sketch. There, that's a rough sketch. Root of pi, omega. Schwartz then asked, what happens as m goes to 0? Well, this is actually a little bit tricky, because as m goes to 0, there's no lab frame. Okay, because there's no frame in which the electron is at rest. So you go to the center of mass frame. So then you have proton and massless electron in the center of momentum frame coming at each other at equal energy momentum. They then obviously have to scatter elastically. So it's elastic scattering. The final energy of the X-ray or gamma ray is the same as the initial energy. Okay, now, then the last part is part D, where Schwartz asked, well, how is this different from what you'd expect classically? And this actually is an important call. This is a plumber. And you take plumbers. Yes, hi. I put the keys to the house in the mailbox. And the red key is for the gate. The other key is for the house. I'll be home around 7. Okay. Good luck. Thank you. Bye. Okay, bye. Plumbers and doctors and dentists, you just can't ignore them.
Well, you can, but at the peril of your sewage system. In all 3 cases.
All right, so let me just review for you. What would you expect classically? Classically, you would expect that this beam of photons is an electromagnetic wave. It hits the crystal of, let us say, lithium or whatever the hell it is, some light element, and all the electrons start moving synchronously, and then they radiate 4 pi to the universe. And so half the radiation is forward, half is back. Suppose it's the crystal is a thin plate, and the photons are just, the X-rays coming in, thin plate, half go forward, half go back. That's what you'd expect. So the final frequency, omega prime, you'd expect equal omega. Compton found omega prime less than omega, except in the forward direction. Compton found most of the photons went forward, not 4 pi to the universe in all directions. And now here's the most interesting thing about this, though, is something that Compton describes very clearly in the abstract of his paper. I actually looked up the paper. Thank goodness it was published in Phys Rev rather than Elsevier, in which case it would be completely inaccessible. And they probably would have destroyed it by now. But instead, you get a pristine copy for free. And what he said was quite amazing, quite lovely. He said, one would expect, I'm paraphrasing in the beginning, one would expect classically that the photon would interact with many electrons in the crystal. Instead, the photon, quote, spends all of its energy upon some particular electron, unquote. And then what is one reminded of? The photoelectric effect, 1905, where Einstein pointed out that you have a beam of red light, very intense, on a plate, say lead plate, and then a detector of electrons. You don't get any knocked off. You go to blue light, even weak blue light, some get knocked off. And it's because each photon has energy h nu, and of course nu is proportional to the frequency. Blue is twice red in frequency. But the point is that the photon doesn't interact, each photon doesn't interact with the whole plate, and moreover, the wave isn't really a wave, it's really a bunch of photons, they're tiny particles, and each photon interacts with a particular electron, and as Compton said, spends all its energy on that photon. So it's something that we can sometimes forget, and that isn't emphasized very much in most books on quantum mechanics, let alone quantum field theory. The idea is that matter is made up of tiny particles, very small particles. The elementary particles are so small we don't even know how big they are. In fact, they might be strings, who knows. On the other hand, what the particles do, well, it's uncertain. The only thing certain is that they obey conservation laws. And with quantum mechanics and quantum field theory, we can predict probabilities, and then in quantum mechanics at least, and I guess in quantum field theory also, these probabilities are governed by wave functions. They're sort of squares of wave functions. But the wave function just tells us the statistics. The particle is not a wave function. The particle is a tiny, tiny particle. And in particular, if you, for example, have a beam of photons and a very dense grating, then on the screen you'll have photons scattered at very far distance. And in fact, if you use a very low beam of photons, very few photons, in other words, and you had eyes that were super, super dark, acclimated, then you'd see one photon there, one photon there, one photon there. And so each photon goes to a very tiny spot on the wall. It's not as though the photon is a wave. All right. Okay, so much for all that. Now back to whatever I was talking about. Yes, well, the next thing is harmonic oscillators. And why harmonic oscillators? Well, it's because of relativity in a certain sense. Namely, that equation, Box. Box is a Lorentz invariant differential operator. And in fact, so if you want a Lorentz invariant differential equation, Box is a good start. And you could have Box plus or minus n squared also as a relativistically invariant differential equation. And well, that, as we'll see, leads to the harmonic oscillator. You remember the harmonic oscillators, mx double dot is minus kx. X is c e to the I omega t plus d e to the minus I omega t. We use a complex notation. Omega is the square root of k over m. H for harmonic oscillator, p squared over 2m plus a half m omega squared x squared. And of course, xp is I or I h bar if you want to stick in the h bar. By the way, feel free to ask questions at any time. I've got all this candy. Yes?
What would be a good question to ask at this stage in the lecture?
No.
Sometimes you want a good question, you know?
No, it doesn't have to be a good question. Any question. All right. Let's look at A and A dagger. A is square root of, and I'm going to put in the h bar. M h bar omega over 2 x plus I p over m omega, and then of course a dagger is square root of m h bar omega over 2 x minus I p over m omega, and since xp is I h bar, you can show, I'm not going to do the algebra, it's not hard, a dagger is 1, or if you want h bar. What is this Hamiltonian written in terms of a and a dagger? Well, it's omega times a dagger a plus a half, and of course this 1/2 occurs for every mode, and so if you add them up, you get a terribly divergent integral. It's quartically divergent. And, well, the vacuum has some energy. It might be what we call dark energy, but it's not quartically divergent, that's for sure. The number operator is a dagger a. We talked about this some last time. N times the state of n quanta is nn. A dagger on n is square root of n plus 1. The state with an extra quantum a, n is square root of n minus 1. The Heisenberg equation of motion for the operator A, which is often called the annihilation operator or the lowering operator, it's equal to the commutator of A with H. Again, we've said H bar equal to 1. This is A with, well, omega A dagger A, because the 1/2 isn't going to contribute anything to the commutator. And this thing is omega times A dagger A minus A dagger A. Almost sounds like you're stuttering here. And this is omega times A dagger A, which of course, since A dagger is 1, this is omega A. So I dot is omega A is e to the minus I omega t A at time 0. So that's how the lowering operator evolves with time. And now, as I said, the simplest let me let's try this one. So the simplest Lorentz invariant equation of motion for a field, the scalar field thing, is just box times the field equals 0. And all right, so this is a massless free field. So this is dt squared minus grad squared b equals 0. We could just set phi of x equal to some lowering operator or annihilation operator for a particular momentum, particular mode, and e to the I p dot x. And so then this would work, because then box phi would be d by dt squared plus minus grad squared on this gives you plus p squared ap of t e to the I p dot x. And if we want this to be 0, then what we want is dt squared ap, or ap double dot, is minus p squared AP, and this was this is of course the harmonic oscillator equation. And so this was for a particular momentum, but we can add them up for all the momenta, and so we can have a field phi of x and t given by d cubed t over 2 pi cubed. I hope my dogs didn't eat the plumber. ACP of t e to the I p dot x plus AP star. So this is basically a classical field because A here I'm taking as just a number, although if we're talking about an annihilation operator, then it's much more than a number, or even a creation, or even a raising operator. All right. So anyway, this is going to turn into a raising operator. This is a lowering operator for mode P, or an annihilation operator for mode P. So it annihilates particle momentum P. This would be creating them. And A of P, of course, has the time dependence that we know about, namely AP of T is e to the minus I omega T AP of 0. So now you see that the time dependence combines with this to give a Lorentz invariant expression here and another one there. And so what we could do, now this is of course one of the problems with Schwarz's metric, apart from the fact that it has so many minus signs. It means that P dot x and the Lorentz invariant one differ by a minus sign. So if we would have phi of x and t then to be an integral d cubed p over 2 pi cubed, it would be then AP of 0 e to the minus I px Lorentz invariant, where px now is p0 t minus p dot x. And so we have the two minus signs give us back this plus sign, plus AP star times 0 e to the I px. So we get these two Lorentz invariant expressions there. Question?
Yes. So why is the natural eigenvalue equation for the box operator interpreted as the mass of a particle?
Well, it's just that if the equation is not box phi equals 0, but box phi equals plus or minus m squared, I forget which, phi, then that is the equation for a particle of mass m, whereas this is a particle of mass 0. And the reason for that is that you see here, what do we have? We have p by dt squared, which is omega squared, is p squared. So the energy and the momentum are the same. That's mass 0. If we had a minus m squared over here, then we would have minus omega squared equals minus p squared minus m squared, or energy squared is p squared plus m squared. That would be the energy, or the energy would be square root of p squared plus m squared. That would be the energy of a massive particle of mass m. So that's why it works that way.
No, thank you.
Really?
I have to get ready for the holiday season. I'm saving up.
In that currency.
Yeah, Halloween is just a few months away.
Okay. So here, omega is the square root of p squared, and more generally, omega for massive particle, p squared plus m squared. And in that case, let's see, this brings down a plus p squared, and so this would be minus m squared p would be the corresponding relativistic equation. And so that would be, the equation would be box plus m squared p equals 0. Still a harmonic oscillator though.
So To make that phi invariant, you have to integrate over time too, don't you?
There's a t here, so it's a particular t.
Oh, it's a particular t.
Yeah. But here, you get a candy. By the way, it's okay to ask a fake question. In other words, if you're just hungry, you can just ask a question to which you know the answer. But here, I gotta get the TAs.
I have a question. Is this phi operator or something?
Good question. Phi at this stage, if A is a number, phi is then just a field, a classical field. If we in a moment we're going to be saying that A is an annihilation operator, then phi is a quantum field. So it just depends upon whether you're talking about how you interpret A as if the basic idea of this quantum field theory is to say that for each mode of the system, we have a harmonic oscillator, and the nth level of that harmonic oscillator means n particles in that mode. Particles. And so in that case, the A and A dagger create and destroy particles.
No, my question was, is phi an operator?
Phi.
Yeah, the whole thing.
Yes. Well, if the A's are just numbers, so that this is just complex conjugate, then phi is just a classical field. To have a quantum field, you interpret this as being the annihilation operator or the lowering operator of a harmonic oscillator, and this a creation operator. So both are operators, not numbers. And then you think of them as the nth level of that mode means n photons or n particles in that mode.
So we are applying this box on some operator.
As a quantum field equation, this is an operator. As a classical equation, it's just a function or a field, a classical field.
So in quantum theory...
How much candy do you want?
No, I just want to make it clear. So in quantum theory, this... I'm
about to get to the quantum field theory. Schwartz makes this very slow introduction, you know, like tide coming in at, you know, where the beach is just almost flat. Actually, I got it completely wrong. The tide comes in very fast when the beach is flat. And in fact, there's a place in France that's famous for that. It's quite dangerous because the land is very, very flat there, and so when the ocean rises, water comes in like nobody did. I forget what it's called. Cathedral there. Every town in France has some cathedral. All right, so let's see. All right, so basically, if we are really following Schwartz, then all that was classical so far. Harmonic oscillator. Okay, so the Maxwell tensor is FAB, and it's an E1 here, and a 0 there, and a minus B3 here. I'm not going to fill them all in. You can look in the book. What's the time? All right, 15 minutes late. Maxwell's equations in the vacuum, dA, FAB is 0, and the other one is epsilon ABCD F, derivative, dA, F, BC, 0. So these are the Maxwell equations in empty space. What's epsilon? It's totally antisymmetric, N123 is plus or minus 1, depending on who wrote the book. But totally anti-symmetric. Lorentz gauge is dA, AA equals 0. Notice that this is invariant because it's a contraction. And because this thing here is dA AB minus dB AA, and so this thing is dA AB minus dB AA, and now this on that is box AB, and then it's minus dB of dA AA. So if you're in the Lorentz gauge in which this thing is identically 0, then the equation is box AB 0. And so that's one reason why photons are massless. So the electromagnetic field is massless photons spin one. The spin one part is another story. But now all massless fields obey an equation of the form box Fi equals 0. Even neutrinos do that actually. It's just that we normally focus on more first order equation, which has more information. Okay, now I guess we're making this transition to quantum field theory, and we say, well, H0 is an integral over all modes, d cubed p over 2 pi cubed, omega p, ap dagger ap plus a half. And omega p, of course, is just p, length of p, because we're talking about a massless field. So each mode has energy h bar omega. Each mode is a harmonic oscillator, each mode meaning each momentum. So for each momentum, we have a harmonic oscillator. The nth level of the harmonic oscillator we interpret as there being n particles of that momentum. And so then we construct what's called a Fock space. And this Fock space, for example, it might have one particle momentum P1, two particles of momentum P2, three particles of momentum P3 or whatever, and so forth. That might be a particular state in the Fock space. I think it was Fock, I'm not sure. This story is, I heard this story ages ago, I might even have been a graduate student. And it was that Fock was hard of hearing. And he had a hearing aid. But he also did not suffer fools gladly. And he was at lunch at Columbia, and he wasn't particularly impressed with some of the people who were having lunch with him, so he just turned off his hearing aid. And that was apparently the way he dealt with people he thought were boring. Obviously, this is not the sort of story you hear at Columbia. I think I heard it at Harvard. All right. Next. All right. So that's Fock space. Now, we have these annihilation and creation operators. So we expect that this is something or other, and this is 2 pi as normalization. If they refer to different momenta, you expect they would commute. If they're the same momentum, they don't commute, so we have a delta function here. So if the momenta are the same, and this is just, what is this? This is a generalization of what we would have if we were, say, dealing in condensed matter physics or ordinary quantum mechanics where we had several harmonic oscillators. For example, if we just had the three-dimensional harmonic oscillator, which is to say a particle in a harmonic potential, then we would say that AI comma AJ dagger would be, I don't know, H bar delta IJ. Well, this is just a generalization of this, and the 2 pi cubed is a conventional factor. Okay, also these creation operators normalize in the following way. If that's the vacuum, then you get 1 over the square root of 2 omega p times p. That's the state 1 photon or particle. And this stuff, we're talking basically in terms of massless particles for some reason. I don't really know why. But it would be the same business whether it were massless or massive. The norm of the vacuum is 1. The inner product, though, of 2 states of different momenta, well, what is this? This thing is square root of 2 omega p times a dagger p, so this thing has to be 2 square root of omega p square root of omega k, 0, ap, a dagger k, 0. Now we use the commutation relation, we see that this is equal to the thing in the other way, the other order, which is 0, because a on the vacuum is 0. And what's left is 2 square root of omega p, omega k, 2 pi cubed delta of k minus p, or p minus k. And of course, since this enforces p and k, the frequencies are the same. So this is 2 omega p, say, 2 pi cubed delta p minus k. 3 vector. Okay. The identity operator for 1 particle states, so maybe I should say 1 sub 1. This is an integral dqp over 2 pi cubed pt over 2 omega p. And again, the same, you have the same formula even if you had mass. Okay, why is this true? Well, if we act 1 sub 1 on the state k, say, what does that give us? That gives us an integral dqp over 2 pi cubed 2 omega p ppk, but then pk is 2 omega p, which cancels, 2 pi cubed, which cancels, delta p minus k, so that's just k. This field, Schwartz sometimes puts a 0 there to say that it's a free field. Anyway, it's dqp 2 pi cubed square root of 2 omega p, and now we have a sub p e to the I p dot x spatial plus a dagger p e to the minus I p dot x, just the 3 vector dot product. But these things depend upon, well, this is at 1 time. As time goes by, these depend upon time with this e to the plus or minus I omega t, which makes this into a Lorentz invariant object. But what's rather cute and comforting is if we take the inner product of p with phi 0 just at x, so everything's at time 0, and then the vacuum, well, what do we get? Well, we're going to have all of these things, and the annihilation part isn't going to count, because when the annihilation part hits the vacuum, you get 0. Okay. So what we have then is P, and maybe I should call this k now. Integral d cubed k over 2 pi cubed square root of 2 omega k a k dagger e to the minus I k dot x vacuum. But now a dagger gives us 1 over square root of twice the energy times the state. And so this is p integral d cubed k over now 2 pi cubed. But this one, it again divides by 2 omegas. So now we have altogether 2 of these two omegas. And this is then the inner product of p with k e to the minus I k dot x. And, well, p on k, the inner product, is 2 omega 2 pi cubed delta function. Well, that exactly cancels all of this. And we then just get an integral d cubed k delta p minus k e to the minus I kx. And that just gives us e to the minus I p dot x spatial. Okay, so let me summarize. Well, there's not much time left, but I guess I have enough time to walk to the front of the room. So what that has told us then is that p phi 0 of x, so we're basically all at the same time, is e to the minus I p dot x. And so we can think of this, we can think of that in some sense, this is like, in quantum mechanics, the inner product of x with p, which of course is e to the minus I p dot x. Actually, the inner product of that is with the 2 pi to the 3 halves here, now that I think about it. And but, you know, apart from this, which is an issue of normalization, it's a similar kind of thing. And so we can think that this thing is that phi 0 of x on the vacuum is sort of like this. And in fact, that's basically true. If we were talking about a general field, though, as opposed to a free field, then the thing that we get here would, we get the 1 particle x state times some normalization, and then we get maybe 3 particle states or 5 particle states, whatever. So we get a little more complicated. All right, I don't think I should go over time, so I'm going to stop basically here. And so, all right, so I'll see you Wednesday. But the following Monday is a holiday, you're telling me. Well, good. I'm on paper for all of this.